Hello guys, today we're going to talk about sigma notation. So we've got section 1.7. This one is one of the honors topics. So let's go ahead and get started. So what is sigma notation? Sigma notation is a shorthand way to write a long sum. So if I wanted to, for example, sum the first 10 integers, and remember an integer is just counting numbers, like no fractions, no decimals. They can be positive, they can be negative, 0 is included. So the first 10 integers would just be 1 through 10. So if I wanted to write out the sum, the long way to write that out would just be 1 plus 2 plus 3 all the way till I get to 10. It takes a while, right? It's kind of obnoxious. So this is called a series. Anytime we are adding a pattern of numbers together, it's called a series. In order to write this identical expression, but in a much more concise way, we're going to use something called sigma notation. So here it is. So notice this symbol here looks kind of like a capital E, kind of a strange capital E, and then it says n equals 1 to 10, and it has an n right here. So this is called sigma notation. It means the exact same thing as this up here, 1 plus 2 plus 3 till we get to 10, but it's just a lot quicker and more concise to write. So let's take a closer look at this on the next slide. So our little symbol here is called sigma, and it is the Greek letter for capital S. Okay, so S for sum here. And let's take a look at the parts of this. So I notice I've made these all different colors. We're going to talk about each one individually. So here are parts of the summation. So the red piece right here, that is, as we know, the sigma. It is the part that tells me I'm going to be summing something together. So capital S for sum, right? It's just in Greek, so it looks like that. That's called the sigma. The index is in green here. So N tells me what number I'm going to be starting with, and it goes up to what number I will be ending with. But N is called the index, okay? So our yellow number here, again, is the starting value of our index. And the purple number up here is our ending value of the index. It means we're going from 1 up to 10. And we just count as normal from 1 to 10. So 1, and then 2, and then 3. We'll start at 1, and we'll keep counting until we get to 10. Okay, the blue N out here, that is the formula. And in this case, it's not much of a formula. It's just N, but it can be other more complicated formulas. But this works too. So basically how this works is we're going to, let me grab a marker here, we're going to take our formula and we're going to plug numbers into it. What numbers will we plug into it? We will plug in our index numbers, and we will start with 1. So the first thing I do is take n equals 1 and put it in where the n is here. So that would give me a 1, right? If I plug in 1 for n, I get a 1. Then I'm going to add on, I'm going to go up 1 in my index, so I'm going from 1 to 2. I'm going to plug it in to n here. I do the same thing for 3, so I'm just starting at 1 and I'm going to end at 10. I'm going up by 1, so I'm going to plug each of those numbers into my formula. If my formula is just n, it's just going to be each number, right, added together. So the sigma is what tells me I'm adding these terms together. And so a plus goes between each one of them. Told me to start at a 1, and then I'm going to end at 10. So again, just like on the previous slide, this is a much more concise way to write all of this. Okay, so let's try some examples. We're going to rewrite each series as a sum. So remember, a series just means I have kind of a pattern of numbers, and they're all added together. All the individual terms in the pattern are added together. So I'm going to be starting with 1. So I have I, that's my index. I equals 1. And then I'm going to be ending at 7. That means I'm going to be counting from 1 to 7. 1, 2, 3, 4, 5, 6, 7. Each of those numbers are going to get plugged into my formula, which in this case is I squared. So if I put a 1 into the formula, that would be 1 squared. Then I go up 1 from there to get a 2. Put 2 into the formula, that would be 2 squared. 3 squared, 4 squared, plus 5 squared. And remember, I'm ending at 7, so 7 will be the last term. I need to make sure I put a plus between each of these. And then here it just told me to rewrite each series as a sum. So it didn't actually ask me to go ahead and add these together. It didn't ask me to evaluate it. It just said rewrite it as a sum, and we've done that. We probably want to go ahead and simplify each of these, actually square them, so we can see our numbers, or we can see our pattern here. But, so there you go. So that is the series written as a sum. So let's try another one. So on this one, this one's very similar to the first one on the first slide. The only difference being is that my index starts at 2 instead of 1, and it ends at 5 instead of 10. So I would plug in 2 to end, just give me 2, then plug in 3, and then plug in 4, and then plug in 5 and stop. So this one would just be 2 plus 3 plus 4 plus 5. Alright, so we're on a roll. Let's try another one. So we've got k equals 0 to 6. 2k plus 3 is our formula. The formula got a little bit more complicated, more fancy or something. I don't know. So we're going to start with 0, and we're going to plug 0 in where k is. So our first term would be 2 times 0 plus 3. Then I'm going to add that to our second term. I'm going to go up 1, right? So I'll plug in a 1 now. So 2 times 1 plus 3. I'll plug in a 2. I'm just putting this extra parentheses so I can see each term and where it comes from. Then I would plug in a 4. Now I'm going to have myself a 3. So there's the next one. Then I would do a 4. And then I can plug in 5. And 6 is the last one I should do here. So that would give me all my terms. That's really nice right there. So now we can take each of these and we can add them all together. 2 times 0 is 0, and 0 plus 3 is 3. I'm just going to write it above here, so this is equal to 2 times 1 is 2, and 2 plus 3 is 5, so that would be my second term. 2 times 2 is 4, and 4 plus 3 is 7, so that would be my third term. 2 times 3 is 6, and 6 plus 3 is 9. Notice I have a pattern going on here. I'm going from 3 to 5 to 7 to 9. Looks like they're increasing by 2 each time. So I could probably, without evaluating these, figure that it went to 11, and 13, and then 15. But we can double check. 2 times 4 is 8, and 8 plus 3 is 11. 2 times 5 is 10, and 10 plus 3 is 13. 2 times 6 is 12, and 12 plus 3 is 15. So our numbers here, our series, should always be some type of pattern. This one just goes up by 1 each time. This one goes up by 2 each time. This one up here is 1 squared, 2 squared, 3 squared, 4 squared. So there is a pattern to each of these. I think I'm going to have a problem here with my fourth example. I kind of wrote big over it, so I'm going to hurry and erase this bottom line here so that we can do our next example. Alright, so our last one on this slide is a equals 1 to 4. So I'm going to start with a 1, and I'm going to go up to 4. And my formula is 2 raised to the power of a. So let's go ahead and plug in our numbers. So first number being 1, so 2 to the first power is our first term. We'll add that, we'll go up to 2 and plug in a 2 for a. We're going to plug in 3 for a, and then we're going to plug in 4 for a. So there's our series. We're going to simplify it. 2 to the first power is just 2. 2 squared, 2 times 2 is 4. 2 to the third would be 8. 2 times 2 is 4, 4 times 2 is 8, and then 8 times 2 is 16. So this series would be 2 plus 4 plus 8 plus 16. Alright, so on this slide, notice we were supposed to rewrite the series as a sum, so we didn't actually have to go through and add our numbers together. On this next one, the instructions have changed. We are supposed to evaluate the series. So not only do we need to write out the terms on this one, we actually need to go ahead and add up our numbers so that we can see what the sum is equal to. Okay? So we're going from 1 to 5. My index starting point is at 1. My ending point is at 5. My sigma tells me I'm summing these numbers. And my formula is n squared plus 4. So I'll start with n equals 1. So that would give me 1 squared plus 4. Then I'm going to go up to 2. So I have 2 squared plus 4. and 3 squared plus 4. So I'm just plugging in those numbers for n. 4 squared plus 4. And my ending term should be 5, so 5 squared plus 4. Now, before I try to add all these together, I want to go ahead and simplify within each term. So 1 to the second power is 1, and 1 plus 4 is 5. 2 squared is 4, and 4 plus 4 is 8. 3 squared is 9, and 9 plus 4 is 13. 4 squared is 16, and 16 plus 4 is 20. And 5 squared is 20. So we've got 20, also it's 25, and 4 is 29. Okay? So our pattern is there, but it's a little bit different this time. 5 to 8, we go up by 3, and then we go up by 5 to get to 13, and we go up by 7, and then we go up by 9. So there's still a pattern, but it's just not like a common difference between each one. It goes up a little bit. And now to get this series, to evaluate the series, we need to add these together. So 5 and 8 gives me 13, and 13 plus 13 is 26. 26, so let's write that down. These three added together is 26. Then we have 46 plus 29 to finish that off. So 40, 50, 60, 75. So if we evaluate this series, we get 75. So this is equal to 75. So just make sure you're paying attention. Is it asking you to evaluate it or just write it out as a sum? Okay? On the ones where we evaluate, we have to do one more step. Okay? Here's a second example. Notice here we have two a's in our equation. We have a times a plus 7, or a minus 7. So I can either just distribute it right now, write it as a squared minus 7a, and plug it in that way, or I can leave it the way it is. It doesn't really matter, you'll get the same answer either way. We're going to start at 0 and end at 3, so I'm going to plug in 0 first. So 0 times 0 minus 7 is our first term. Second term, we're going to plug in 1, so it'd be 1 times 1 minus 7. We're going to go for 2 times 2 minus 7. And we're going to end on 3, so this will be our last term, 3 times 3 minus 7. Okay, again, if you wanted to just plug it into a squared minus 7a, you'll get the exact same thing. Either one works. So since 0 is on the outside here, we're multiplying everything by 0. That term is just going to go to 0. 1 minus 7 is negative 6, and negative 6 times 1 will be just minus 6. On the third term, we have 2 minus 7, which is negative 5, and negative 5 times 2 is negative 10. And then on the last one, 3 minus 7 is negative 4, and negative 4 times 3 is negative 12. So if I sum these all together, I'm going to get negative 6 minus 10, which is negative 16. And then minus 12 more would be negative 28. So there's our sum. Okay? So let's just try one more. I'm going to change colors again really quickly so that we can keep our work separate on all of these. I could have put an equal sign in there. 49 minus k. K is going to start at 2 and it's going to end at 5. So 49 minus 2 plus 49 minus 3 plus 49 minus 4 and ending on 49 minus 5. So 49 minus 2 is 47 plus 46 plus 45 plus 44. So that would give me 160, 170, 182. Okay, hopefully I did that right. So 182. Okay, so we're going to go ahead and we're going to try something just a little bit different. Okay, we're going to start with our series written out as a sum, and then we are going to use sigma notation to rewrite the sum so that it has, or sigma notation, it has a formula. Okay, so notice here it says, to write a sum in sigma notation, try to find a formula involving a variable. I used k as an example here, but it doesn't have to be k, it can be any variable, where the first term can be obtained by setting k equal to 1, the second term by k equals 2, and so on. So let's look at an example. So here we have 2 plus 4 plus 6 plus 8 plus 10 plus 12. So we need to find a formula with k in it that when I plug in 1, so when I plug in k equals 1, I get a 2. When I plug in k equals 2, I get a 4. When I plug in k equals 3, I get a 6. So it looks to me like each of these numbers is just k times 2, right? So I can rewrite, let's write my sigma here. I want to start with 1. I don't always have to start with 1, of course. You could start with another number. The important thing is to make sure when you plug that number in to your formula that you're going to put over here, that you get the first term. When you plug in 2, you get the second term. When you plug in 3, you get the third term. If it started at 0, then I would want to have, when I plug in 0, I would want to get 2. And when I plugged in 1, I would want to get 4. So it doesn't really matter on your index where you start and stop, as long as you are getting these numbers each time for each term that you plug in, and it matches. So this looks to me like it's just 2 times k. So if I plug in k equals 1, I'm going to get 2. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. And it looks like I'm going up to 6. That's my last term. It would be 6 times 2, which is 12. So this would be the same sum, right? They're equal to each other, but written in sigma notation. Okay, so let's try another one. I've got 1 plus 2 plus 4 plus 8 plus 16 plus 32. Okay, so what I need to do here is I need to think about what pattern is actually happening. So it looks like every term is being multiplied by 2. This is 1 times 2. Sorry, this is not 1 times 2. This is 1 times 2. 2 times 2. This is the previous term times 2. So I guess it would be 2 times 2 times 2. 3 times, and then this will add another times 2. So it looks like I'm multiplying 2 every time. So if I can write this another way. I can write this as 2 to the first power, 2 squared, 2 to the third power, 2 to the fourth power, and then 32 would be 2 to the fifth power. To get a 1, I could put 2 to the 0 power, right? 2 to the 0 power does equal 1. Anything raised to the 0 power is always equal to 1. So for my sigma here, I could just start my index at 0 and go up to 5. That would work. K equals 0 to 5. And my formula would just be 2 raised to the power of k. Because the first one I would plug a 0 in, I would get a 1. Then I would plug in 1. 2 to the first power is 2. 2 squared is 4. So that works perfectly. If I did want to start my index at 1, I can still use this formula. The only thing I would have to change, well, a couple things I'd have to change actually. I would have to say that this is 2 to the k minus 1 power, so that when I plug in 1, I still get that 0 exponent to give me a 1. And when I plug in 2, because this is my second term, I would still get 2 to the first power, because 2 minus 1 is 1. So if I want to make sure it starts on the index, or make sure the index starts at 1 and goes up from there, I might have to adjust my formula a little bit. These are both perfectly acceptable answers. I still need to figure out my last number here. But if I'm plugging in 0, sorry, no, this is going to move to 1. If I plug in 1, 2, 3, 4, 5, 6, then I would want to go up to 6 instead of 5 here. I've adjusted my index a little bit. These are both equal. They're equivalent. They're both correct. So it doesn't matter where your index starts necessarily, unless you've been asked to make sure it starts at 1 for some reason. But just to let you know, there are like a little bit, sometimes there's a little bit of difference in them, but they can still mean the same. They can still equal the same thing. Okay, let's try one more. So we have 1, 8, 27, 64. So the important thing here is to look for a pattern and to figure out what's really happening, to figure out what index will work. It looks like these are cubes, so 1 cubed is equal to 1, 2 cubed is equal to 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. So you really need to find that pattern, like what is actually happening, and then you need to see what numbers are going up one at a time, because that's going to be your index. That's going to help you figure out what your index can be and what your variable should be in your formula. So here's sigma. My index is going to start at 1. And again, I don't have to use k every time. I can use any variable to represent my index. So this is term 1, then term 2, term 3, term 4, and term 5. So we're going to go from 1 to 5. And my formula is just going to be k raised to the power of 3. Okay, so there's my formula. These are equal. So just go ahead and practice some of these. Give them a try. If you have any questions, let me know. And thanks, guys. Have a good day.